and so this is equivalent to A vector dot B vector over the norm of A vector. So this is another version of the representation of a scalar projection of B vector onto A vector. So we can either write that as the norm of B vector times cosine theta, or A vector dot B vector over the norm of A vector. But it is critical to remember that this is the scalar projection of B vector onto A vector. So if you're using this one, you're using the B vector. If you're using this one, and the denominator is the norm of A vector. Okay, so that's a scalar projection. So let's look at an example of that first. But both of these, remember A vector dot B vector is a number and the norm of A vector is a number. So this is also a number. Okay, so scalar projection gives you a numerical answer or a constant answer. Okay, so let's just see if we can look at an example. Be able to write. So example. Well, let's let A vector equal 1, 2, and let's let B vector equal 3, 4. And if I want the scalar projection of B vector onto A vector, two different ways that we can do this. I could figure out the cosine of the angle in between. So I could say norm of B vector times cosine theta, but I'd have to figure out what cosine theta is between those two vectors. And by the way, I could draw these up. So over 1 up 2, if I do the position representation, there's A vector, and if I go over 3 up 4, try and find that angle in between. Those weren't very good numbers to pick, but anyway, I think that one's a little more vertical. Anyway, but there's an angle in between, or I could do A vector dot B vector all over the norm of A vector. So I might do this one instead. That seems to be a little bit easier. So A vector dot B vector, once again, we're going to multiply the corresponding components and add the results. So 1 times 3 plus 2 times 4 is 3 plus 8, which is 11, over the norm of A vector. Of course, the norm of A vector is the square root of the sum of the squares. So the square root of 1 plus 4, which is 5. So that's going to be 11 over the square root of 5. So the scalar projection of B vector onto A vector is 11 over the square root of 5. Now I could also do the scalar projection of A vector onto B vector. So let's just do that. If I did the scalar projection of A, instead of B vector onto A vector, I'm going to do A vector onto B vector. Well, that's a little bit different because then these switch. So that'd be either the norm of A vector times the cosine of the angle between them. Remember, A vector dot B vector is the same as B vector dot A vector, so I could switch those, but it's going to be the same dot product. But that would be A vector dot B vector over the norm of B vector. So in this case, it would be norm of B vector is the square root of 9 plus 16, which is the square root of 25, which is actually just 5. So the scalar projection of A vector onto B vector is 11/5. So it is a little bit different on how that works out. Okay, so now let's go to vector projections and figure out what those are. Okay, so defining a vector projection. Basically, what I want to do is I want to kind of show you how this works here. But if I have, I'm just going to draw 2 different vectors. So this will be A vector and B vector. Well, I'm gonna use B for blue, or let's call this B vector, and then A vector, red apple. Okay, so I'll just go this way. And then what I'm going to want to do is I'm going to want to project B vector onto A vector. And so if I drop that down 90 degrees and get a 90-degree intersection and call that, let's call that point R. Let's say this was the origin, so we'll call that point R, or point the origin. And then, so this vector right here, if we drop B vector down, now B vector would actually note, you know, that's an arc. So if I dropped it down, B vector is actually longer than the perpendicular intersect here, because OR, the side OR, does not have the same length as, you know, if I call that OB, as this length over here does it. So notice that just dropping the vector down is actually longer, but we're talking about a vector projection of B onto A. So vector projection of B vector onto A vector. So what we're going to want to do is the vector projection which is actually purple in my picture, the vector projection of B vector onto A vector. The question is, how are we going to do that? So that's the purple, actually. It's the purple one there. But what we're going to do is we're going to take the scalar projection. So it's going to be the scalar projection of B vector onto A vector times a unit vector in the same direction as A. Okay, times the same in the same direction of unit vector in the same direction as A vector. Okay, so what is the vector projection? Well, one way to say that the vector projection of B vector onto A vector is the scalar projection, which one of the representations was norm of B cosine theta, and then times a unit vector in the same direction as A. Remember, the unit vector in the same direction as A is just A vector divided by the size of A vector, right? So this is going to be time, that's not a, I don't want a dot there. It's not a dot product. So anyway, it's times A vector divided by the norm of A vector. So this is one result, one definition of what the vector projection of B vector onto A vector is. Okay. Now you might wonder why that's the case. So let's kind of look at this. What is the length of the blue one here? The length of the blue one is the size of B vector, which is just the norm of B vector, right? And of course, theta is the angle in between A vector and B vector, right? And then if I say, hey, this vector OR has a length of L. If I call that L, what do I know? I know that the cosine of theta is the adjacent over the hypotenuse, right? Adjacent over the hypotenuse, which the adjacent has size L, and the hypotenuse has size norm of B vector. So if I want to solve that for L, what am I doing? I'm just taking B vector, the norm of B vector times cosine theta. And so that's what this is. This is actually the length L there. So I've got the length of vector OR times a unit vector in the same direction, and that gives me that vector. So that's what the vector projection of B vector onto A vector is. So we can do it like this. Now I am going to clear this out because I'm out of room. This is why I need a bigger board. But anyway, so we had the vector projection, which I can write like this, the vector projection of B vector onto A vector. And so I'm going to put the one that goes on as a big one, and then onto on top of, so I'm going to put subscript of A there. But anyway, what we said is this is the norm of B vector times cosine theta times a unit vector in the same direction, which is A vector over the norm of A vector, unit vector in the same direction of A. Okay, so this is what we came up with last time, but we also know what the cosine of theta is by a theorem, right? So this is going to be equivalent to B vector, the norm of B vector, times, instead of cosine theta is A vector dot B vector over the norm of A vector times the norm of B vector. So cosine of theta by a theorem equals what's in parentheses there, and then times the unit vector in the same direction of A is A vector over the norm of A vector. So let's see what this ends up being. Well, if you notice, the norm of B vectors, those are scalars, those would cancel out, and then the number part, A vector is not a number, it's a vector, but the rest of these, A vector dot B vector is a number, the norm of A vector is a number, and the norm of A vector is a number. So I can write the numbers out front and write that as, this is equivalent to A vector dot B vector over the norm of A vector squared, and then times A vector. All right, and if you want to put parentheses around that part as the number part, the scalar part, you can. But anyway, this is the vector projection of B vector onto A vector is given by this. Notice that basically the denominator has the A, and then it's times A vector. So we're going on to A vector. So let's just note that if I had the vector projection of A vector onto B vector, okay, then and if I'm drawing that, if here's A vector and there's B vector, then basically I'm coming up here, right, and it's this is the vector projection right there. So if I had that, you know, what does my formula look like? Well, we could say B vector dot A vector, just switch all of the A's and B's, but you know, dot product is commutative, so I could just keep that as A vector dot B vector, but in the denominator it'd be the norm of B vector quantity squared times a B vector now, times B vector, because I'm putting it onto, whoops, forgot my vector. I'm putting it onto B vector. So it's the scalar that we get with A vector dot B vector over the norm of B vector squared times B vector. So, okay. So let's look at a specific example of this. All right, so example. I think I have an example, maybe. All right. I'm going to do a different one than I have in the notes. So we're going to let A equal the vector 2, -4, 5, and B vector. So these are vectors. B vector is the vector -2, 1, 0. Okay, so if I have these, if I want the vector projection of B vector onto A vector, then what's that going to be? Well, it's going to be A vector dot, let's just write the formula, A vector dot B vector over the norm of A vector squared times A vector, right? So it's the scalar number part, which is this, times A vector. All right, so let's just figure out what this is. What is A dot B? Well, once again, multiply the corresponding elements and add the results. So this is going to be in parentheses. 2 times -2 is -4 plus negative 4 plus 0 is negative 8. Okay, so you can double check my work on that. And then the norm of A quantity squared, well, let's figure out what the norm of A vector is. It's going to be the square root of the sum of the squares. So that'd be 4 plus 16